I'm going to be scared shitless just by the sheer sound of it.
Yeah, it's pretty scary.
I should not volunteer.
Okay, so let me, this is buffering here. Give me just a second.
It's not like I have any words to complain.
Okay, I'm just waiting for this to buffer really quick. So as I start this, if I don't remember to click this button, then my voice will start talking over myself. Here it is, almost ready. Sorry, it's taking so long here. It's taking a little bit longer than. Okay, so let me, this is background here. All right, so I got to stop that, otherwise I hear myself twice. All right, so hopefully, if you're looking right here, this is a Tesla coil. We'll learn a little bit more about this, but there's a solenoid. This is a very loosely wound solenoid. Those are going to turn out to be things called inductors. Down inside here, there's some capacitors. You probably can't see them. We've got this shielded here just so they don't have big bright sparks blinding you. So the idea is Nick is standing inside a Faraday cage, and that Faraday cage is connected to ground. So the idea is this Faraday cage, since it's a conductor, even though it's not a solid piece of metal, should prevent any electric field from going on to him, right? If you remember last time, you guys saw we talked about this a little bit. So without further ado, let's just give it a shot. All right, so here we go. So luxuriously run your hand up and down on the middle of the, is that a little scary?
Oh, maybe just a little bit.
Let's try to get it.
Oh.
Yeah, sometimes this thing's a little quirky, so you're gonna have to do it quickly.
Okay.
So you can go ahead and run your hand up and down right now. Do you feel anything?
No.
Yeah,
No.
So there we go. Let's give him a round of applause.
Oh, God, there's 4 other people in the room.
Yeah, it's kind of a strange scene.
Oh, that's horrifying.
Yeah, do you want to try the glove too for kicks? Here, let's do this. This is also fun. So Angus, you want to take this out of here and I'll just catch you later. The thingy's up here. If you want to shut the door off. Hey, those of you on Zoom, let's give Angus a round of applause. Yeah. Oh yeah, well actually, you're not going to see it because I'm not
built
looking at
this
the
fine
screen.
cage, everybody.
That's right. Angus built this thing. Oh my gosh. You need help, Angus? You good?
It looks like something straight out of salt.
Actually, we had some students create it, and when they built it, they didn't measure the door.
Oh.
And so the first version was larger than the door, so we could never fit it out of the class. So we had to tear it down, and Angus did all that work. You got it, Angus?
I think so, yeah.
All right, thanks, Monty. All right. Okay, let's try the same thing with his glove. All right. So this is just kind of fun to do. All right, make sure that stays connected in there. Put on the glove. All right. Make sure that's the thing that's closest to the Tesla coil, right?
Yeah.
All right.
Oh,
Yeah, it is. So it's just metal glove. So then, all right. Rotate it so that the camera can see the sparks, all right? And I'm going to turn out all the lights just for a second. Angus, I don't suppose you want to get that door full.
Yeah.
What's up, Vince?
I just heard you do something. It
Yeah.
sounded interesting, so I popped on over.
Check it out, some Tesla coil. Here we go. All that good. So,
Did you feel anything?
yeah.
or maybe
so-
the slight vibration, but that's a moment.
All right, so this is pretty cool, right? The Tesla coil. This is just
Your
more
camera
dramatic.
feed just cut out.
Oh, what's that?
The camera feed cut out.
The camera feed cut out. Huh, that's weird.
Did the test?
Oh, it didn't tight to the light switch, maybe?
Great.
Oh, wait.
Oh,
wait. It might, the camera feed might be tied to the light switch. Or maybe.
how about that?
Hey,
That's
There you
weird.
go.
Were you able to see the sparks?
It cut out like right as it started.
Oh, I wonder if that sent some
Yeah.
kind of remote signal somehow, right? So
No,
this is very high frequency, although it's good. We'll go to this other version. All right, so let me turn this off. Let me do this. So obviously you don't want to do this at home unless you kind of know what you're doing. The key is in all of this, we've had a good ground on all of this. So I don't know if you remember, I don't know if I said this, but ground is where we're going to call 0 volts. So the earth is an endless reservoir of electrons. So if we can get the electrons to go there, we don't have to worry about the earth filling up with electrons. We can just keep dumping them there in perpetuity. So now in this case, I just like to show you some demos when I can, and this is a fun one. We'll learn more about why this thing works at the end of the semester, so maybe we'll bring it back later. But now I've got this one. Let's see if this works. Now, this might not seem obvious at first, but we can think of this as a point charge, right? It's going to be a metal sphere, but we know that spheres are approximately a point charge. Let me do this. Out of the way, so I'm not thinking about it while I'm doing this other one. So in this case, oh, and then Angus has got the wand here. Let's verify that this one's working today. So again, this is now grounded, right? So if the electrons jump ship and come over to this conductor, they should go through here and back into the ground. So let's see. Does it take a while to warm up?
And I think all the way up is high speed on this one. This one.
Oh, that's so undramatic after that last one.
Yeah.
Oh. All right, I'm giving up. Man, this has been like the Van de Graaff semester from heck. We'll worry about that later. It's kind of frustrating. Well, the fun part about this one, I'm going to explain the demo and not really go too far into it. Imagine this is a point charge, right? And imagine I'm holding this light bulb. I've got a video of me doing this some other time, and I'll send that to you after class. But the idea is you can get this thing to spark, even though it's not on there. Just having trouble right now because we're like, well, I suppose we might as well try it. I gotta be careful now. So it's taking a long time to build up charge. So maybe what I'll do is I'll close this door while I've got a second. All right. And so if we can even get a slight flicker out of this thing, that would be good. Trying not to trip. You see anything at all? What are we gonna do? Angus, you want to get on that door? Just leave it a tiny, tiny bit cracked so I don't trip over stuff. All right, so here we are. You see it lighting up ever so slightly? Okay, so usually it's so much more dramatic than this. I wonder if we're got humidity again today. But the idea is, if you look carefully, the part that's lighting up depends on where my hand is located. Right, so now see how almost the entire bulb is lighting up? Versus right here, this part is not doing anything. All right, that's pretty good. So it's oftentimes much more dramatic. It just seems like we're just having bad luck. I don't know. I'm gonna turn the lights on here. Oh, I should make sure. This probably has a lot of charge on it now. Is that what it is?
Yeah.
Okay, so it's probably one of those factors again. So this is
around here somewhere.
what's that?
You want Pythons?
No, that failed last time when it was like this too. So I'm gonna give up on this. And actually, Angus, I could just let you roll all of this out of here if you want. Is that okay if I just dump that on you?
Totally, yeah.
All right. All right. So I wanted to, this actually has something to do with lecture today. You wouldn't believe it, but it does. I don't know if this one went off, Angus. I didn't see it. But I'll start talking about this up on the whiteboard. Okay, those of you on Zoom, hopefully you can still hear me. And if I screw up the screens, I tried putting in a bunch of presets on here. Let me do some blue tape here just so I can find this. I don't know how this is going to work. That's about right. What's that?
We should go onto this board, like put a screen up in the back, so you can see the Zoom simultaneously.
That would be a good idea.
Or like,
Yeah.
or just have like a TV in the background that they can hook up to the computer.
Yeah. Whoops. Let me hit this other one. Sorry, it's learning here. Angel, you're on Zoom. You can tell me how far over to go. Oh, is that about right? Somebody that's on Zoom?
Wait, for field of view?
Yeah. Can you still see the purple?
Yeah, you can keep going over more if you want.
Okay, tell me when.
Keep going, keep going, keep going, keep going, keep going, keep going. Right there. A little bit more to the left, 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 left. Right there. That's fine.
All right, that's just for me to mark so I know where not to go, right?
And you still have like an inch left.
Yeah, that's pretty good. That's pretty good. All right. All right, so we'll try this out. Okay. All right, we'll try this one. All right, so the idea behind these demos, whoops, there we go. Let's suppose we had that Van de Graaff generator. I'll just call it Vandy. This is effectively like some plus charge, let's say. For some reason, let's say I chose a plus charge. Okay, gotcha. You don't have to do it now. That was all I needed. But yeah, if you want to stay on, that's cool. All right, so let's say we have this Van de Graaff with a plus charge. And this is the fluorescent light tube here. We'll call it the F tube, right? What do we know about electric potential? Well, does anybody remember the equation for electric potential for a point charge? And I think you could answer via Zoom by unmuting or.
AQ over R.
Yeah. All right. So here's the idea. This is really the simplest thing. We've got radius 1, and then wherever I put my hand was radius 2. So let's say this is where I put my hand. The idea is there is a potential difference. This is going to be voltage 1. This is going to be voltage 2. The idea is there's a potential difference, delta V, between the two ends. And that is what we saw when the bulb was flickering between my hand and there. So in that case, you could think I was acting as the grounding wire, which is a little bit weird, right? I was acting as the source of electrons for these things flowing through there. So anyways, I thought that would be just slightly fun to see a practical application. And I hope you agree, this is supposed to give you some sort of belief in this equation might be real, that the voltage depends on position near a point charge. And that's what that was supposed to be about. Any questions about that? That was just for fun, basically. All right. Now, let's try a question. Let's start with 24.6 on page 65. 24.6 on page 65. All right. This is by far the weirdest class I've ever taught in my life. I don't know.
Weird fucker like the star.
I know. Very strange. How are those markers showing up on Zoom, people? Okay.
It's all right. The black's a little light, but I can see it.
All right.
Looks great to me.
All right. I think this is that same bad black. I forgot to get a new black marker. I did? Okay, maybe it's another crappy black marker. All right. So 24.6. So we've got some point charges here. Whoops. That looks kind of crappy. We got a minus charge, a plus charge, plus charge, and a minus charge. And part A is asking for voltage at center. All right, so here we are at the center. What do you think should be true about the voltage at the center? What is this? This side of square is A, I think. Is that right? Yeah, so is this. So it's a square. What should be true about the voltage at the center?
0? It's 0?
0. The idea is this distance, if you do the math, actually ends up being A over root 2 because it's this side and this side. Those are A over 2, A over 2. Do some Pythagorean theorem, you get this result. But isn't that the same distance to right here? And right here? and right here. So the idea is we expect V total to equal V1 plus V2 plus V3 plus V4. When we do that, these two should have plus and minus and cancel. These two should have plus and minus and cancel. All right. Part B, the electric field at the center. What is that going to be? This is kind of a review question. Somebody else, I think that was Jesse last time. What do you think should be true about the electric field at the center? Anybody have an idea? How about we start? Is it 0 or is it non-zero? What's your gut tell you?
I'm thinking 0, but
0.
yeah.
Okay, so this is the case. So with the potentials, all that matters is the distance. With the electric field, you're right to be a little confused because it depends on the direction, right? So in this case, this is going to pull. We could say that's E1. This one's going to pull, and that one's going to cancel out. So E1 and E4 are going to cancel. Similarly, if this is number 3 and this is number 2, E2 is going to push away, but E3 is going to push back at it. So we would expect the electric field at the center should be 0. This is not always true. All right, the electric field at the center and the voltage at the center are not always going to be 0. Case in point, what's the next question, right? It's the, I'm coming, there we go. Now what happens if the bottom 2 charges are switched, right? Yes, so what's going to happen, this is 24.6 part C. If we switch the bottom 2, how's that going to affect the answer for voltage?
Stay the same?
Should stay the same. The voltage is 0. What about the electric field?
That would change.
Yeah, because now we get this one's pushing this way, this one's pushing that way. This one's pulling that way, this one's pulling that way. The net result is 1, 2, 3, 4 of the horizontal component. Something like that. Is not equal 0. All right. I like to think of it like this. When I throw a marker up in the air, you know that velocity is 0 at max height in the y direction, but acceleration is not. Similarly, just like a sub y is equal to d vy dt, we know that the electric field is minus the gradient of the voltage. But since we don't know what the gradient is, sometimes I'll say the electric field at the x is minus the derivative of the voltage in the x. Just like this one, you can have one of these be equal to 0 while the other one is non-zero. Same thing applies down here. Just watch out for that on test A. Sometimes I'll throw you a bone like this and just ask what thing is equal to 0, E, V, or both. So hopefully that's kind of a good warm up to get our brains thinking again. Any questions on any of this before we keep cruising? All right. All right, let's see here. Let's go on to, let's see, what do we want to do next? Let's talk about 24.4. And I'm going to try and fly through that one pretty quickly. A little bit of this is some review of topics, but I think there's a purpose to do this. So I want to look at 24.4 at the top of page 65. 24.4. I'm going to erase and get ready. Those of you on Zoom, what is this? How is this experience for you so far? Is this weird?
Better than last year.
Better than my old little mini whiteboard?
Exactly. I can see everything.
Oh, that's a good sign.
Yeah, you got some professional camera movements.
Yeah, you like that?
Pretty
Let's
nifty.
That's Max. All right, whatever. Just having some fun. Yeah, what's that? I think I got it now. Yeah, so I added some presets last time, so hopefully I can quickly get to those now. All right, what did I say we're doing? 24.4?
Yeah.
All right. So we've got basically a positive plate. And we've got a negative plate. We're told the spacing between them is distance D equals 5.00 centimeters, I think. We're going to put a plus charge in here. Plus charge. And it says there's an electric field inside with magnitude 1,000 newtons per coulomb. All right. So in this case, I want to say a couple of things about this. Because we're in chapter 24, we might talk about voltage. I want to make clear that 1 Newton per coulomb is equivalent to 1 volt per meter. So 1 volt per meter, 1 Newton per coulomb, same thing if you need that. All right. Now, I said this was the electric field. This is technically not the electric field, but the electric field magnitude. Let's say I want it to be an electric field vector. What direction do you think the electric field is inside of here?
To the right.
Down right, yeah, to the right. So we expect. So I could stick an I-hat on there if I really wanted to. So far, so good on that. In this case, is the electric field, is it reasonable to assume the electric field is constant inside of there? Is it reasonable to think the electric field is constant? Does anybody remember what we talked about last time? That was a long time ago, it was a week ago.
I don't think it's constant.
It is okay to be constant as long as these plates are really large. Do you remember that we said inside of parallel plates? There's a formula on the back of your workbook. I'll show you where it is approximately. Right there. So on the equation sheet, right down to about 7 rows or 4 rows or something, it says that E of the parallel plates is actually constant. So it's only true if we're near plates. That's parallel plates. It's constant given by this change in voltage over the spacing. So that's going to be something we use in just a minute. So if you recall, last time we talked about this briefly, that is something we're going to use. All right. That. Don't want to forget that. All right, so now let's go ahead and read through this problem. Determine the force on the particle. For part A, we're supposed to get the force. What equation should we use for getting the force?
QE.
Yeah, force equals QE. Now, in this case, do we know what the charge is? Did it say it was a proton? Yeah, it's a proton.
Yeah.
So Q of a proton is equal to positive E. Remember, E is 1.602 times 10 to the minus 19. So that's the magnitude of the charge on an electron, but it's also the magnitude of the charge on a proton. So far, so good. Now, in this case, we know both of these things. I argue the force would be pretty easy to get, so I'm not gonna do it. So far, so good? Okay. How are you guys doing it here? Is this too weird for you or is this working? Yes, no? Okay, all right, all right. Yeah, it's such a strange experience. Okay, now I said, find the work. Does anybody remember any equations that talk about work from any physics class? What's that?
Like,
Uh,
or wait,
power is joules per second.
uh,
Work is force times the derivative of distance, right?
Something like that. I'm gonna write it for you. The integral of force dot ds.
Yeah.
I think that's where you were going, and was that what you were thinking too, or
I was thinking like the non-calculus.
which is, what's the non-calculus? Do you remember?
It's like
Force,
or distance cosine.
yeah, exactly. FD cosine theta.
Yeah.
So now, let's check here. What was theta? What does theta mean?
The angle in between
Yeah, in between what?
the two plates.
No. The
Oh,
angle
the two forces.
the force and the ds.
Yes.
So here, in this case, isn't this thing going to move this way?
And the force is in that direction as well. So it'd be 1. So it'd just be force times distance.
Yeah, so in this case, sorry, I gotta catch up. You said the force is that way as well, right?
Yes. ds is in the same direction.
Yeah, so in this case, we'd expect the angle should be 0.
Yes. And that would
And
be
what's the cosine of 0?
1.
1. So then in this case, it's just FD, which we know the force. Now notice it's the magnitude of the force here. Here's the force vector. If you wanted to, we could say this is QE in the I hat dotted with DX in the I hat and do that crap. But basically it's going to be QED with no I hats because the I hat dot I hat becomes 1. Same idea. All right. You know what Q is. We have a value for E. We have a value for D. What might you need to watch out for if you plug in numbers?
You have to take the magnitude of E.
Yep. Got
Oh, we
that.
did. Okay.
What else?
The
Units.
distance, yeah, it's not in the units that we need.
Yeah, so watch out for the units. When we're doing this problem, remember, a Newton per Coulomb is a volt per meter. Since D is in centimeters, it's probably not going to make sense. I would convert this to 0.05 or whatever. You know, that's all I wanted to watch. Watch out for units when you're plugging in numbers. I think that's enough on that. Okay. C, final kinetic energy. All right, so I'm going to try this one for a sec. I don't know if you're going to be able to read. Whoops. Wait, which one? It's 3. So this is going to be a little bit small for a minute, and then I'll zoom in just a second. But for C, I'm supposed to get final kinetic energy. Any equations we remember that relate to that? Maybe that relates to work. From perhaps chapter 7 of Physics 161. Maybe you
The
remember.
initial equals the final?
Say again?
Is it kinetic initial equals kinetic final?
No, no. I was
What,
looking for
B squared?
work is equal to change in kinetic energy. Maybe you don't remember that one. This is pretty obscure, right? So, or maybe I said it this way. So this might have been the K final minus K initial. I promise to zoom in a minute. The only thing is I need this work equation. So probably you have it written down. And now I'm going to take this equation from the work from part B and bring it over there. Which one was I doing next? No, this one. There. Wait, no, this one. Okay. So the work from part B was QED. And then what's the initial kinetic energy? If I could go back over here. Oops. What was the initial kinetic energy of this thing? Did it say?
From rest, so 0.
0. So this term goes to 0. Released from rest. So this, hey, there we go. We got it. That's the final kinetic energy. All right. D. All right. Final velocity. Now, how do we get final velocity out of this? What's kinetic energy equation?
One half mv squared.
The 1/2 mv squared.
Oh, now it's switched. So-
What's that?
Oh, I thought it was 1/2 MB squared before, so I thought it switched. Now it switches.
Yeah. So yeah, exactly. We knew usually we skip part C and just go right to the final speed, right? So out of this, V final is equal to 2QED over M square rooted. Whenever we're doing physics, we should think about the plus minus signs on a square root. Do I need to worry about that for this problem or not? I need to read the question. Part D says final velocity. If we're looking for final velocity, I need the vector, right? Will I use the plus or the minus for this particular problem? Well, if I go back and look at it.
Plus.
Plus, because I'm going to the right. So it turns out it didn't really matter. But it's worthwhile to think about it. It's plus in this case. In the I hat. All right, that's great. And then to be honest, what do we always do when we're doing velocity? We ignore this and we ignore this and we say we're assuming the I hat and the vector symbol are there. So a lot of times you won't see the vector or the I hat when we're writing. Sup, Dom? This is the weirdest class ever. It's on, there's like, I'm trying to, it's very strange to me. Anyways, yeah. Anything you want to say about electrocuting students in cages? Okay, we already did that, so we're good.
Okay, there were, what, 4 of them here earlier?
Well, Angus.
Someone got electrocuted?
No, they survived. Yeah, you're right. All right, talk to you later, Dom. All right, okay. Part E, all right. So part E, if I could, I think we need to go back to the first, we're on the first board. Part E is asking us about the electric field, no, the voltage, sorry. What does it say? I don't know if you can tell. This is very distracting it's hard for my brain. Maybe I'll get used to it. We'll see. Okay, part E, determine potential difference between the plates. All right. I want to be careful here. We're looking not for potential, we're looking for potential difference. This goes back to that light bulb experiment that I did at the beginning that barely worked at all. Potential difference is the voltage difference. All right, so in this case, that's right here. Potential difference is a delta V. It's not V, it's a delta V. I hope you agree. Oh, I should be careful here. This side has a vector on it and that side doesn't. We want to talk about the magnitude is equal to this number, right? So this should have been a magnitude at the beginning. I apologize. Well, I hope you agree that delta V is just ED in this case. V equals ED, I sometimes say. All right. Now, relating again, you probably saw me with the metal frame here and we had the glove and we were grounding it. So what does ground mean? Okay, if I could use this picture, I need to erase some stuff. If I could go over here, am I on the right screen? Yeah. So in this case, oh, I think I had force was equal to QE. I need that later. That was part A. Okay. The idea is what we're going to do is we're going to choose to call this ground. This is a fancy way of saying this is at 0 volts. Okay. So if this is at 0 volts and this potential difference, delta V was ED, and I want to be clear, the absolute value of that potential difference was ED based off solving this equation for delta V. That means this plate would be held at voltage ED. Now this is subtle here, all right? To be clear, ground is wherever in the circuit we choose to call ground, all right? Now, for a lot of circuits, ground is like the plug in the wall, the ground in the wall electric socket. So when you're doing normal experiments, usually we don't get to choose ground. Whatever's connected to the ground at the wall, we call ground. But in this experiment, you could actually do all kinds of weird stuff. But I'm going into this weird colored marker. This probably won't show up that well. But you could call this 0 volts if you wanted. And that might make this positive ED over 2, and this would be negative ED over 2. Now I know this isn't going to show up too well on the Zoom, but the fact remains, think of the 0 volt line or the ground in a problem, sort of like our reference level in chapter 8 from energy. You could choose to call the bottom of the whiteboard height equals 0, or the top of the whiteboard height equals 0. When you do physics problems, the changes in potential energy are what matter. Similarly, you could call this side ground. You could call that side ground. You could call the middle ground. You can call anywhere you want your reference level of 0 volts. Now, if we call this side 0 volts, this side would be negative ED. If we call this side 0 volts, this side is positive ED, or like I said. So just be aware that wherever we call ground, it's just an arbitrary reference point. And again, in real life, you usually don't get to have that much choice because real life devices are plugged into the wall and we want to use the wall ground. All right, I think that's enough on ground. Any questions about that?
It's basically like where you want to set your coordinates, your axis.
Yes, it's your coordinates, but for voltage.
Yeah.
That's a good way to say it. Yes, I like that. All right. Now, where am I going with this? All right, part G. I'm going to show you this problem another way using this other whiteboard here. So let me switch over to this one. I just want to do this problem again using our new technology of potential and voltage, right? So all that stuff that we just showed was the old way of doing it. Here's the new way of doing it. Imagine you go into a lab, right? We go into the lab, we have 2 parallel plates. Normally, the first thing you do is you say, oh, I'm going to set this to ground or 0 volts. And then you connect these 2 plates to a power supply, and we crank up the voltage so that this one is at some voltage. Now, how do you know what voltage to use? Well, I know that V is ED. So what I do is, if I know the plate spacing and I know the electric field I want, I tune the electric voltage or the electric potential to the appropriate value that gives me the right electric field for the correct spacing. If you know E and D, I turn up the voltage to the right number to get the right electric field. Then you have your proton sitting here. I know that V initial equals 0. This is a lowercase v. It's the speed, right? Now I could do an energy problem, right? U initial plus K initial plus work external or non-conservative equals U final plus K final. All right? When I do it this way, well, let's first pick off some things in here that are equal to 0. So at least one thing's got to be equal to 0 here.
K
What was
initial.
that? K initial, all right. That's going to go to 0. I'm going to give you a tip. This also goes to 0. We don't have to worry about drag or friction or zombies with ropes. So I'm going to ignore this term. All right. How could I get U initial now? U initial is the charge times the voltage initial. Got it. Ching. If I say that, maybe you could tell me another thing that's equal to 0.
U final.
U final. If I use 0 volts here, this is Q times 0 volts. That goes to 0. So now what do I get? I get Q times V initial, the initial voltage, not the speed. Oh, this is crazy. Equals 1/2 mass speed final here, right? So notice this is voltage, this is speed. Now we see why we have to keep our V's separate. When I do it this way, I hope you agree, we're basically back to the same thing that we found earlier. All right, so we do get the same calculation as earlier. All right, questions on this process? We're doing an energy problem instead of having to do forces, work, and then do an energy problem on top of it, right? If we use this new definition of potential energy as Q times the voltage, it's very easy to do this for practical things in a lab. Voltage is something that's easy to control with a dial. This is going to be sweet. All right, part H. Suppose we instead did an electron starting at the negative plane. Put an electron here, put a proton here. All I want to know is what would change and what would be different. So let's kind of start. Would the electric field change? And maybe I'll go to the full zoom so you guys can see. Oops. Okay, that's worse, I think. All right, well, let's take a look. Over here, the electric field was to the right, the force was to the right, okay? Are these going to change? Yes or no?
Electric field, no. Force will change direction to the other way.
Let's see here. There we go. So we expect the electric field always points from high voltage to low, or plus charge to minus. Since this is a negative charge, force equals QE. Now I get a negative sign in the charge, so the force is going to be backwards now. So what is that going to do to the work? If I flip the sign of the force, will the work flip sign as well?
Yes.
No, because now we're going the other way, because ds also flips. Do you agree?
Okay.
In the first problem, we were going, the force was to the right, and we were moving to the right. Now the force is to the left, but we're also moving to the left, so I still get the same. It's still positive. All right? So what about the final kinetic energy? Will that change?
No.
Same. What about the final speed then?
No.
Yes, it will be changed. Because the final, remember, what happens here is, what happens if you use an electron? How does an electron compare to a proton?
An electron's negative. Its mass is
Mass.
significantly smaller.
Yeah, So it's about 1,800 times smaller. If the mass drops by 1,800, a factor of 1,800, what should happen to the speed?
It should increase
By what factor?
1,800.
No,
Um,
square root of 1,800 because there's a squared there. Does that make sense? Think about it. If this goes down to 1,800 and each of these goes up by the root of 1,800, then you'll get a square root of 1,800 times square root of 1,800. The squared quantity will go up by 1,800, which will exactly balance this out. Did that make any sense?
sorta.
Basically, because there's a squared here, it doesn't go up by the same factor that this one goes down. How about I say it that way? This one, there's no squared on it. This one there is, so do some math. How about that way? Yeah, so basically plug in some numbers before you trust it. All right. All right, so I think that's pretty good on 24.4. The idea, what's our kind of big picture here? So there's a couple of things to see in this problem. One, this energy method will be a nice way to do problems if we just want to learn about something's final speed. In this problem, we used a special case of parallel plates where the electric field was constant inside. What's cool is this method that we showed on this page will work whether you do this with parallel plates or whether you do it with point charges or a point charge near a rod or any kind of weird ass thing. Right? So this is going to be a stronger method in general because we don't always have parallel plates. The other thing, watch out for this mass issue, the mass of the electron and the mass of the proton. You'll see similar problems where you get very different speeds because the mass does show up as soon as the speed is what we're calculating. So in all these problems, watch out. Now the mass matters. And a final thing, always watch out when you're writing. Keep clear whether you have a capital V for voltage or lowercase v for speed. That's going to happen a lot. I think that's good on that problem. Good? Okay. All right. Let me check the time. 30. All right. Let's go ahead and try 24.5 right now. Okay. So take a look at 24.5 while I get the board ready. What's that?
Because at least from memory, we like left over slightly when we were working with which word? It's DS.
DS is an infinitesimal amount of arc length. So, for example, if you're traveling straight to the right, DS would be dx in the I hat. If you're going straight up, it'd be dy j hat. If you're going around in a circle, it'd be r d theta theta hat. Is that what you needed?
Rough.
Okay. Basically, how about I tell you to you like this? In general, ds is equal to dx in the I hat plus dy in the j hat plus dz in the k hat. It's however much you're moving in x, y, and z space. Right, but for physics at this level, usually what we do is we say you're either moving to the right or you're moving up, or if you're moving in a circle, well, I'll call that the theta hat direction, and I'll say that your distance is r d theta, and you've seen r d theta a couple of times already. So if we're going around in a circle, we'll choose one of these and do simplified problems where we do basically one of these three, but not all at once. If you're doing full 3D calculus, this would be ds. You've probably seen this before. Let me go over here.
I think one of a few of our problems. It was one of the, I see it in the problem, I just don't know.
Yes, yes, and I'm gonna keep doing it all semester long and eventually it should be locked, okay? But ds depends on the problem. That's why I write it as ds, because it, yeah. Is that good enough on that for now? All right. Now we're going to 24.5. Right? 24.5, I think that's what I said. All right. We've got 3 electrons, I think. 1, 2, 3. I'm going to number 1, 2, 3. I know the distance between them is a. All right. In this case, we're showing the initial state. It says find the initial energy stored in the fields. So we're supposed to get what variable? V, U, E, F, F, U?
U sub I.
Yeah, good. All right, so in this case, U initial. What's the next step? If I have 3 point charges, do you remember what I want you to do if I'm trying to get U total?
Add them up.
Okay, what terms am I going to add up? All right.
U12,
Yeah.
U13.
Except now, because it's initial, I'm going to stick an I. That's what I was hoping to do. Does that make sense?
Oh, yeah.
All right, so sorry about that. We add up all the different possible pairs. That was the idea, is we add up all the possible pairs. Which one of these charges has that energy? Which one of these charges has this amount of potential energy? It's shared between all of them. Good. It's not like this one has it or that one. It's stored in the electric field energy. So it's not, this was something that came up earlier today. The potential energy is not located somewhere. It's just shared in the electric fields amongst all of them. Okay. All right, good. So in this case, what do you think? Should it be, well, let's just do it. K, negative E, all over. What's the distance between 1 and 2? A, a Canadian's favorite distance. Next, between 1 and 3.
2A.
2A.
Yeah, so that's what you got to watch out for. Just because the spacing is A, sometimes different charges, this one will be 2A. So there's just the little things that would screw up your whole problem and make you lose credit, right? And then the last one. Two and 3 is A. If I do the math on that, I believe that's 2.5. Because I could factor out a K E squared over A in each term. They're all positive because I get a negative times a negative. And then I get 1 plus a half, which is 2.5. All right. What do you think would happen if you release these things from rest? If I just let this go right now as it is, what would happen?
The center molecule would stay place, and then 1 and 3 would go opposite directions.
These two, right? So you could imagine this one would push this way, this one would push that way. These ones would have a force outwards, and they would push, and we would expect these two to go outwards, and this one to stay there. Now, okay, that's cool. I like to think of this as, because this potential energy is positive, we expect these things should start flying away from each other and escape. Okay? So that's what the sign of the potential energy means to me. Now, in part B, we are told that these two are fixed in place, I believe. So what we're going to do is we're going to put these two, we're going to hold them in place somehow with a laser trapping system. All right. These are held in place. If that's true, what should happen to 3?
It should shoot to the right much faster.
Okay. If I wanted to learn how fast it's going after it travels a long distance, what's the general strategy we did with energy problems? I see there's an energy problem. I've got a before picture. What was the thing that we usually did right afterwards?
So for the after picture.
After picture. So I'm going to do that somewhere. Now, I think it would make sense to do it right here. So I'm going to write this answer up here. Just give me a minute. U initial was equal to 2.5 K squared over A. All right. All right. So in the after picture, I still have 1, still have 2, Whoops. And then 3 is like way over here, right? And it's going to be moving pretty fast. All right. You probably can guess. If I want to learn about V final, what's the next thing I might write down? Or what's something you would write down? You might write down something differently. There's a lot of different ways we might approach, but what's something you might write down? If I want to find speed, what type of problem do I do?
Energy,
Energy. So I know, what do I write?
U sub I plus K sub I plus W non-con equals U sub F plus K sub F.
Okay. Now, let's go through and drop in the zeros. I'll take care of this one for you. Unless there's some particularly weird example where there's a charged object that's got friction, we usually assume this is negligible. What's the initial kinetic energy?
Should be 0, correct?
Yeah, what gave you that idea?
At rest?
At rest. Initially at rest, right? We know U initial, agreed? What do you think U final is?
Would that one be 0 too?
You would think so. And I've seen it written on almost every final exam every year, and it's wrong every year. Is there a pair of charges that are still close to each other?
Yes.
This energy term doesn't go away. You see what I'm saying?
I see.
This is the one everybody forgets. This still has some of the energy, right? Because the energy was stored amongst all 3 charges. This one still has some too. So U final would be K E squared upon A. Now, to be clear, radius 2, 3 is approximately equal to infinity. So that one doesn't contribute. Radius 1, 3 is approximately equal to infinity. So that doesn't cause a contribution. Remember, because it would be plus something over infinity plus something over infinity. So those other terms are there, but when you divide by effectively infinity, they both go to 0, right? All right. Okay, so at this point, now I know this term right here, and K final is just going to be 1/2 mv final squared, same as the last problem at this point. What do you think? So far, so good?
Yep.
So that was the thing I wanted people to watch out for. Everybody thinks the final potential energy goes to 0. A lot of times with these point charge problems, that just doesn't happen. All right. Any questions about that while I zoom out? If you're curious, on page 66, we did the demos already, but if you look at 24.7, I think I mentioned this last time. I said something about the Rutherford quotes. So I've got those written there, the Rutherford quotes. And so when I'm reading them, I'm assuming you on Zoom can read it on your own too. But the quote is, "It was quite the most incredible event that has ever happened to me. It was as if you had fired a 15-inch shell at a piece of tissue paper and it bounced back and hit you. It's crazy, like launching bowling balls at tissue paper and they fly right back at you. It's ridiculous." But that one is that is the experiment that helped us see that the nucleus is probably a very dense positive charge, right? So that was the big signature experiment. But if you look at that one, maybe I'll draw it up here and put it on the board really quick if I can remember. Wrong board. There we go. Spin it around up here. Looking for these. Oh, there. This problem is a little bit different because there's only 2 charges. So in this case, if you have a plus charge here and a bigger plus charge here, right? In this case, U initial equals 0. For this one, it makes sense because there's only one pair. So that's why in this one, the example you see in every textbook, the initial energy is 0. If there's more than one pair, like the last problem, you might not, okay. And then so in this case, it comes close. U final equals non-zero. In fact, actually, it's K Q1, Q2 over the distance, where this is the distance, right? And up here, initially it's moving. So this is a variation on that same problem. You start out with it moving, and then here V final is equal to 0. It's the same type of problem. But you can get a limit on this distance. If you know the two charges, if you know the initial speed, right? We know K initial is something like 1/2 m V initial squared. If you know the max, the initial speed, and these are things that could be figured out, if you know the two charges, we could get a value for D, the spacing. And that gives you an upper limit on the size of the nucleus. So this was a big deal. And the fact that this happened blew people away. And I love the other Rutherford quote there. All science is either physics or stand collecting. Talk about unbridled arrogance. I love it. Cracks me up. But this is why people hate physicists, right? When you talk like that, they don't like it. All right, questions about this one. This was problem 24.7 effectively. I just did it wrong. We can see, though, a pattern. These are quick to do if you use energy, right? Setting the initial energy equal to the final energy, figure out which terms are 0, and then you can do a quick energy problem and solve for some letter. Okay, good? All right. Let's go ahead and take a short break. I think it's a good time to take a break. What is it? Yeah, all right. So let's do that. Oh, my goodness.
Oh, sorry, you weren't.
I'm just like hanging on, like this, so it's fatiguing me so much thinking about it, but
I totally understand that.
I'm just trying to,
You can open it.
I've been working on just making sure I could do this tonight, and then I was gonna think about it.
You need to understand stuff.
Yeah. Well, I mean, the labs, so I don't know. I was talking to another instructor, right? And all these instructors are saying they're getting the emails like COVID's canceling class, right? Or they're saying like half the class is quarantined. And so it's like, well, and if anything, COVID's rising in this area, right? So I think right now it's still pretty low risk, but.
Well, it's just that everybody's going to party all over the place.
Yeah, and I mean, just whenever Delta hits, just depends on your geographic location, right?
Yeah.
So, I mean, the prudent thing to do would be to minimize the amount of time we spend in boxes breathing the same air for 3 hours at a stretch, right? That's the smartest move from a public health perspective, right? So at the same time, we have to weigh the benefits of not having to do Canvas quizzes and the frustration, because that just makes everybody drop and makes me quit too.
Yeah.
I don't know, it just weighs me down every day. I don't know. You guys are lucky you don't have to make this call. Yeah, it's funny, the data from the survey, about 80% of people want all face-to-face all the time.
Yeah.
Which, if my kids were vaccinated, right, they're too young to get vaccinated. That would be a big game changer for me. It would, right? I worry like about saddling them with a long-term. Yeah. Oh, I'm reading your guys' chats in the Zoom right now too. I don't know if you knew that. Oh, the Mu variant. Yeah. I don't know. I mean, it's such a tough call. Part of me is like, if these lectures are decent, I'm almost thinking about making, because I feel like this is a noticeable improvement. What do you think out there on Zoom, people? What do you guys feel?
This is much better than trying to follow on your smaller whiteboard.
Yeah.
But I mean, it's still like doing it on Zoom and being asynchronous, kind of asynchronous. Like we could still talk to you, but I mean, I don't know. It's still harder than being in person, I think, but it's not as bad, so it's okay.
Yeah, because you can see the layout of the room. I don't know if you noticed. I can't look at you guys on Zoom at all, and I don't see anything in the chat that you guys are doing. So if you're sending me stuff in chat, it's like you gotta unmute, which I know for some people that's a challenge to be able to unmute because of the reality of what's going on at your house, Yeah. But when you got, it's strange too, when there's the in-person people here, like I felt like I was neglecting them because I don't know, but it's also weird because there's only 3 of them here. So it's like, it's so awkward for them because like, I don't know. It's just a strange experience. Like, I don't know. So I'm reading Jacob's comment here. Yeah, but I mean, for me, I could see doing these lectures on Zoom, but then labs and exams in person. I was looking at a calculator from Duke, and it was saying based off this square footage and the number of air recirculations per things and the number of class meetings and the number of students and the number of HEPA filters or whatever you got running, and you could do all the math and it would spit out a probability of infection. And it said if I basically do this all in person, I think it said something like 7%. Now, who knows? There's a lot of variables in there, right? So maybe I didn't punch in the right square footage. I was just an estimate. So so I'm like, man, that's a 1 in 14 chance of coming down. That's not necessarily the best odds. And it said basically a 7% chance for students as well. Whereas it, right, so it's directly correlated to the quantity of time we all spend together, but I don't know. And then with the other teachers telling me there's all these outbreaks in their classes now, right? And then they have to quarantine and go ERT anyways. I don't know. I don't
That
know.
happened to, I think that happened to one of Valley's classes where someone taught it until they had to cancel the whole class, now they're ERT again.
Yeah, yeah. And he thinks it's just a matter of time till we're all ERT again anyways, but God, I can't imagine that. That's just, but yeah, we'll have to at least do exams in person and I think labs. I don't know.
Parking lot.
How do you guys feel in the lab? Are you guys worried about the lab in terms of airflow and stuff? Compared to, like, this room is kind of sketchy, I think.
Okay, like standing right here.
I'd rather do labs than code.
Yeah, got it. The
I
one-
think there's positive pressure up there, so like it's just being blown out.
Yeah, I gotta have you keep that mask up there.
Yeah.
But yeah, what were you saying, both of you?
Airflow is a bit sketchy, because like I'm standing right here, don't feel it, if not slightly on my legs, and that's about it.
Yeah. I mean, maybe I should get another air filter in here, but I'm trying to imagine on test day, about half of these seats would be filled, right?
We'll probably disrupt airflow a little more too.
What's that?
Let that disrupt airflow a bit, we'll have like all the bodies in here.
Yeah. But I mean, the
Parking
main
lot,
thing
yeah,
is
so-
you could build a nice, high quality filter with a box fan and, right, you put a box fan here and put 4 filters here, and then you gotta have a cutout to restrict the airflow at the corners. But for like $150, you can put these cubes in here at various places and you like massively beat these little dinky ones they've got, right? You can get 600 cubic feet in an hour turned over for each one of these cubes, and you can put these high quality filters on them. And so that would probably be pretty good. But like just a cheap box fan like that with some filters and some cardboard, you can make a high quality filter. Whatever, we should get back to work though, right? All right, sorry. Yeah, a level. Just reading Jacob's chat here, really, yeah. Yeah, I'm they're trying to force me to pick something. I'd like to have a little bit more flexibility, kind of ebb and flow with the transmission rates.
I don't know, negotiate for like or not like a quota, but like a ratio.
They've been talking about this for 2 years and it's still there's no good solution, right? There's nothing you can do other than take your chances. But I mean, obviously, if we're all vaccinated and wear masks, then it's pretty good, right? But I got the high quality Johnson & Johnson. So like, maybe that makes me a little more gun shy, right? I don't know. It's like, but my kids are in school too, right? And so it's like, I don't know, it's just a numbers game. It's just, I don't know. It's not the most fulfilling way to live, as we all know. I digress. Let's focus on some physics. All right. So if you've got your workbook out, I've got pages 66 and 67 open. I just thought I'd point out some ways we can mix things up. So some common geometries that we use on test questions are squares and equilateral triangles. And so if you're not familiar with the geometry of the equilateral triangle, you probably should figure that out. So if this is S and this side is S over 2, you could use this angle as 60 degrees to figure out the height. And so, right, once you do that, a common mistake is thinking that the center of the triangle is halfway over 2. And so you can see on these 2 pages, there's a couple of pictures of equilateral triangles and squares. Something that happens with this is you can either have.
Hey, Jorstan,
Yep.
could you zoom in on the left board?
Thank you.
Thank you.
Forgot I didn't do that. So. And this could happen to either of these two cases. Right, so the ways that I might mix this up on a test day is you could have 4 point charges in a square. I guess I could leave one of these corners off or something. You could have a triangle. You could have some of them be positive, some of them be negative. For example, if you look at the top of page 67, right? If you look at 24.10 versus 24.11, right? So maybe I'll just do this really quick. So just this simple case, like if we compare 24.10 to 24.11, in this one, we say the bottom two charges are fixed. So I'm going to hold these in place. I think that's done in both. If those charges are fixed in place, what's going to happen to this one when you release it from rest?
Fly upwards.
It's going to fly upwards. What's going to happen to this one when you release it from rest?
Fly down, then get pulled back up.
It's going to oscillate back and forth like this, right? And so these are the kinds of things that I might mess with you, right? And then I might say, what is the speed of this proton when it gets to the center of the triangle? So you have to do some geometry. Why? That geometry probably is better for your career than some of this silly charge moving around, right? You got to know triangles, squares. For example, with squares, we always have this stuff. If this has side length A, right, you know that this is A times square root of 2. But then we also saw earlier that this distance, this is not very square-like. We see that this distance right here, if I do it with the squirrely line, this was A, whoops, over root 2. So from a practical standpoint, just be aware that there's some geometry, there's some plus minuses, so very similar looking problems will exhibit very different behavior. This one would probably fly off to R equals infinity, whereas this one would go to height equals 0. They're just different types of problems. So with these problems where we're doing U initial plus K initial, I guess I'll make it clear that for all these problems, we're usually doing U initial plus K initial equals U final plus K final. In all of these problems, you got to remember the U's, you have to add up every possible pair. And sometimes, like in this case, there'd still be a pair left in the final energy state. So a common mistake on final exams has been people forget to account for this having some contribution to U final. Whereas in this one, they all three contribute to the initial and possibly the final. All right, so, all right, I think that's enough on this part. Any questions about these kinds of problems and the ways I might try to trick you? I mean, I guess I could try and do a circle too, but whatever. Circle is everything has the same radius. Yeah, those I usually do with electric field though. All right, good on that. So on the bottom of page 67, all right, physics and chemistry majors, you pretty much have to do this problem. Okay, it's such a big deal. We could sketch this one out here and maybe let's just get this one started. Let's not finish it, but at least show you how it works out. So I'm going to look at 24.13. All right. And whoops, I'm going to go to the other board. 24.13. Okay. I got a minus charge, so 24.13. I got a minus charge. I got a plus charge. These are separated by some distance A, I think. And now I'm going to go out here to this point, P. Okay. And the idea here is there's a radius here to point P, which I'm going to call R negative, meaning for the negative charge. Whenever I have two point charges, one plus and one minus, I usually label the R vectors as R for the negative and R for the positive. Now, does anybody remember what we call a plus charge and a minus charge in close proximity like this?
A dipole.
A dipole, right? Two poles, like a north pole and a south pole. So the dipole is huge in chemistry, all right? Now, to be clear, there's a vector R. Now, in this case, I guess you could probably guess this distance here is A over 2, and so is this distance here. All right? So what's interesting here is we can actually rewrite R plus in terms of this. A vector this way plus the vector R. And we could rewrite this vector as a vector that way plus that vector R. Said another way, R minus as a vector is equal to, this is A over 2 in the I hat. Plus the purple R vector. Now, if you wanted to, we could actually call this A over 2 in the I hat plus X in the I hat plus Y in the J hat. Where notice, if I go from the center here, this vector R is just the XY coordinates to get to this point. So notice we get something that looks like X plus A over 2 in the I hat plus Y in the J hat is the R minus vector. Now, if we're trying to learn about voltage, we don't need the vector. We only need the magnitude of that. And so we see that you get something like X plus A over 2 quantity squared plus Y squared raised to the 1/2. Something like that. I'm going to pause for a second. That's a lot of stuff. Does that make any sense? Is that good? Kind of. Again, what I'm trying to do is I'm saying this vector right here, maybe if I get some more space. Right? This is A over 2 in the I hat. And I see that this vector plus this vector, if I do tail to tip, that adds up to this vector over here. Right? So this vector plus that vector adds up graphically to this vector. Well, what I'm saying is this vector plus that vector, well, here's another way of writing that. And then I just get the magnitude. It's the x part squared plus the y part squared and then square root. Is that a little better?
So it's like the purple R, not like an R.
This is the vector from the origin to the point that we care about. Why are we doing this? Because in chemistry, usually you say the distance from the molecule to a point that you care about. Well, the molecule is usually from the center of the molecule. Right? And so what we're doing is we're rewriting this vector, R minus, in terms of the distance from the center of the molecule. Now, you may not see it right away, but I hope you agree that R plus is going to look very similar, except isn't there a minus A over 2 in the I hat?
Yeah.
And so when we do that, it's going to be very similar, except for a minus sign right there.
Yeah, what was like fancy masters that just makes sense here.
Yes. Well, give me just a sec here. So R plus would be very similar, except we're going to get a minus sign right here instead of a plus sign like this, which is kind of confusing because the minus charge gets a plus sign, and the plus sign gets a minus charge, but so be it. All right? At this point, it's pretty easy to write the electric potential. V total is K negative Q over R minus plus K positive Q over R plus. And this would get you the voltage at any point in space, right? Now, when we do this, I don't know if you can see this, but when you plug this crap into there, you might say, huh, this looks almost like I could use a binomial expansion. So this is one of those problems where I go into depth on the binomial expansion. Right? Are there other ways to do this problem? Sure, but this is one way. So at this point, you could skim over the solution and see what you can learn from that. If I was going to do this on a test, usually I simplify this dramatically. So I feel like this procedure of seeing how you write these R plus and R minus is really useful for a chemist or a physicist, right? But if you look back at problem on page 64, problem 24.2. I hope you agree that problem looks very similar, except I labeled Napomo and Lompoc instead of point P. Right, so on page 64, that shows you ways I might make this easier for a testing. Now, sometimes I would even use minus Q and maybe plus 2Q or something. But so the procedure here might be very similar, where you have to get these R vectors for different point charges. That particular problem is so huge in chemistry, I feel like we had to talk about it. All right. All right. At this point, if you just plug these things in, I think you've got it. All right. And so you can look at a solution for more on that if you need it. I think that's pretty good. What do I want to do next? All right. Any questions before we go on? All right. You know, there's other things you can do too, right? If this vector is much, much larger than A, right, you could maybe do some other tricks in here. You could factor this out. And so you see you'll get an x squared plus a y squared. I don't know if you see that x squared plus y squared term is going to be R, or R squared, this R. And so then you could say, oh, I'll let you look at that later. All right. Let's move on to page 72. All right. So in particular, I'm going to look at 24.18. 24.18. Give me a minute. Point 18. Right. Okay. Got some total charge Q. All right. We want electric potential at origin. I believe that's what we want. Okay. So if we want the electric potential at the origin, what is this symbol? What letter do I want? F, U, V?
V?
Yeah, that's V. Okay, and I hope you agree that V is the integral of dV. Meaning this. If I want the total, I add up all the little contributions. I'm going to say that again. If I want the total, I'm going to add up all the contributions. Well, you know what to do. Tell me what to do. What's
Gotta
one?
pick a DQ.
Pick a DQ. Here it is. There's my DQ. All right. Then what?
Our limits start from A. Oh, yeah.
Yeah. Okay. So this was labeled in the picture. I'm just throwing that there. You were saying there's some limits. What are the limits?
It's A and then A plus L.
Yep. And so, right, that's why I drew this arrow, because the smallest limit is where A is where it starts. L plus A is where it ends. Good. What did we do with this last time?
It's going to be DE DQ over R, right?
Okay, so remind me, let's start like this. I think you got it right. What was V for a point charge? What was the equation of V for a point charge? K,
KQ over R.
KQ over, yeah, okay.
yeah, KQ over R. So now, if I'm going to build this up out of little point charges, what's dV going to be? You said it, K
DQ over R.
dq over R, right? Well, before I do the integral, and we know, like, I'm going to keep these limits here, A, L plus A. What was dq? Do you remember when we did this problem before?
Lambda dx.
Lambda dx. What is lambda for this problem and why?
Q over
Q
L.
over L because it's uniformly distributed.
How do you know it's uniform?
Because it says so.
Ah! And if it didn't say so, we would assume that, right? The only time it's
Right.
non-uniform is when it explicitly says it's non-uniform. So if it says it, so you just said lambda equals Q over L, charge total over length total. So far, so good? Let's hit it. Oh, what's the R vector mean? What does
X,
R vector mean in this equation, like in English, in words?
X I hat.
No, like you're right. That's the R vector. Kind of, well, careful. It's
It's
from what
the-
to what? I guess that's what I'm looking for.
The vector from the source DQ to the POI, which is the origin.
Except this is an absolute value, right? Because it's the we don't have to worry about the R vector. Technically, the R vector is not X in the I hat because it has to go from the source to the POI, which would be negative X in the I hat. But you had the right idea. In this case, when we just need the magnitude, R is just X. If you're worried about it, you could even slap an absolute value on there, okay? If you're saying, well, what if X was a negative? Well, we're not doing that. All right, so in this case, for this problem, we don't need the absolute value because we're sitting in the positive quadrant, all right? Well, when I do that, that's the integral, isn't it? R, the distance, is X. dq is lambda dx. This is going from A to L plus A. So I'm going to pause for a minute. Any questions about what I did here? If it helps. That whole thing is dq, right? This, just right here, is lambda. Lambda dx. what do you get when you do that integral? Woods.
ln
And
x.
I was gonna say I'm walking, I trip over a log. Okay, so it's K Q over L ln, but physicists never say ln, they just say log, right? So if a physicist says logarithm, they mean natural log unless otherwise specified. So, all right, so if we say log, I mean natural log. And then when you stick in the limits, it's always going to be upper minus lower, but then you can do the logarithm trick and say this is upper divided by inside of the logarithm. Like that. What are some things we should check? That looks kind of like a Q there. I'm going to make sure this is an A. What are some things we should check with any answer?
Units.
Units. Well, compare this to that. K should be on top, Q should be on top, meters on bottom for voltage. KQ meters. Does this thing have units?
No.
It's a function, no units. Looks good. And this is why it's usually advantageous to express your logs as a quotient inside. All right. So, okay. Feeling good on that? What do you think will be different in 24.19? Go ahead and think about it. We'll get it set up there. This button. I'm going to erase this. 24.19. Ring. All right, we're sitting up here. Here's my point P. How would you attack this one? Trying to get the electric potential, right? V is equal to the integral of dV. We're going to add up all the contributions. What are we going to build this thing up out of? Are we going to build it up out of rings or point charges?
Point charges.
Still going to use point charges, right? So I'm still going to have K dq over R. What does the R vector mean?
Radius.
From what to what?
The ring to the point of interest.
Yeah, so we got to go in and up. So that's the R vector, right? That's not capital R. So R is not equal to the ring radius, right? It's from the source dq to the point of interest. In this case, what is the R vector? Or sorry, what is lowercase r, the distance for this particular dq?
Pi r squared times h. Or would we include a cosine?
Nope, nope, not that. I
Okay.
just need the distance from here to here. Well, what's this distance to the center?
Pi r squared. Or
No,
just
no, 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 you're overthinking. It's
r.
negative r in the r hat, right? You're just going in, this distance is capital R, right? That's the radius of the ring. And then what was this distance up here called in the problem? This distance right here.
Z.
That's Z. So I'm going to add in Z in the K hat. Did that make sense, Cole, or not?
Sorta.
You're going inwards on a circle is negative R hat. So I'm going radius R inwards, then Z upwards.
When do we add in the I hat, J hat, and
You
K hat?
could. Oh, I see what you're saying now. Okay, so this one, I think now I understand. This would be cosine theta in the I hat. And that might have been what you were talking about, right?
Yeah, because on it it includes the coordinates. So I figured.
Yes, yes. But now, the reason I wrote it this way is because I don't technically need all this stuff, because if I go to a different angle, shouldn't the distance still be the same? So if I went from this DQ, wouldn't I still go inwards and upwards?
Yeah, at any point it's going to be the same.
And so that's why we don't need this way of doing it. You're right, that would have been a correct way, absolutely. And notice it's negative, so it'd be negative in the I hat and negative in the J hat, but depending which angle, the angles could flip the sign of it. But in this case, what matters is the magnitude of the distance should be this squared plus that squared. And if you're not sure, you can do that for this, and the angle drops out, right? Because you get a cosine squared plus a sine squared every single time. So then it ends up being that the distance is what matters. Is that better on that one now? Now that I understand your question. That's weird. I'm like staring at the mic, waiting for you to speak.
Yeah.
Experience. I feel strange. Yeah. All right. Are you guys good with that? Okay. What's DQ in this case? It's not lambda dx anymore, is it?
No.
What do you think, Nick? Putting you on the spot because this relates to a question you asked earlier. I don't know if you know that.
I think yes.
This is where you would use that ds that you asked about earlier. I don't remember when we asked that.
Yeah, after.
Yeah.
Yes.
So, right, because there's a small bit of arc length.
Yeah, so I'm wondering about that. Okay, so everything's small for Earth length, so yes.
And this for a circle was, do you remember what this was? It's not your d theta.
R.
R d theta, yes. Right, what is lambda for this problem? It's charge for total length, right? But length doesn't make sense here.
No, because it's a ring.
So what's the total length?
The circumference?
It's not r d theta, it's the circumference. You guys know who was the roundest knight at King Arthur's table?
R.
Circumference.
Well, I was going to say Lord Faticus, but that works too.
All right. Anyways, I think you agree we've got all the pieces here, right? Now look at this. When you plug this stuff in, is this going to be a tough integral or one of those easy integrals? Take a second to look at it. Easy, why?
Most of the stuff are constants.
Yeah, is capital R a constant?
Yeah.
How
Yes.
about Z?
Yeah.
How about 2 pi and Q? Yeah.
Yeah.
So pretty much everything in K is, so when you plug it in, the only thing that's changing is theta. So everything's gonna pull out. K, this, in this problem, this pulls out, and we get basically an integral over d theta from 0 to 2 pi. You want me to just show you the integral real quick, just for completeness? Sure.
Yes, I'd appreciate that.
So let's plug it in. It's going to be the integral of K, lambda is Q over 2 pi R. And then this is times ds, which is R d theta. So all of that is dq. Then we're dividing by and our integral is over d theta, right? D theta is what we're integrating over. So in this case, if I'm integrating over d theta, my limits need to be, well, if I start here and call this 0, what's all the way around? 2 pi, because we have to use radian. We wouldn't use 360. My limits are going to be from 0 2 pi. And now you can see what pops out, a bunch of stuff. You would theta integral, the 2 pi's are even gonna drop out. This is one of those ones that's got an answer on the back, look for it. I don't know if you can see that, but the 2 pi comes from the integral and cancels the 2 pi in the lambda. So it's right there, about 7 lines down, second column. Good? All right, how we doing on time? Oh, sheesh. All right. Well, take a guess what we're doing next, 2420. Let's look at that one. Okay, I'm on this board now. So weird.
So wouldn't this be the exact same problem, except for there would be no, just the ring would be the washer itself?
Give me just a second. Give me a second. Let me
Okay.
get it drawn up. So everybody kind of think about, there's something subtly different here.
The lower half?
Give me a minute. Problem is this? 2420. There's my disk. That distance is Z. This distance right here is capital R.
Yep.
I know I want to get the total electric potential, so I know V is equal to the integral of dV. I'm going to add up all the contributions. My question is, are you going to build this thing up out of point charges?
No.
Rings.
No, that's different, right? We're going to build this up out of rings. That's what we're trying to build this thing up out of. Well, so I don't need dV of a point charge. I need dV of a
Washer?
ring. Well, do you remember what we did for that last time?
The angle of it, right? Or would it be the radius? Minus that radius.
I would use the formula on the back of the equation, the answer that we just derived in the previous problem for a ring. How about this? What was V of a ring? Remind me.
KQ over parentheses R squared plus Z squared,
Yes.
1/2.
So now I need to use dV of the ring. So I know I'm going to have a K. Instead of a Q, I'm going to have a
DQ.
DQ. Let's all go get blizzards after this. Okay. That was my Dairy Queen reference. It totally fell flat. Next, what do I have in the bottom? Let me say it this way. Why should I not write this? Why is that a bad idea?
So that's the radius of the entire disk.
Yeah, so that's not my ring radius. So now that needs to be some other radius. What's a good name for this radius in the problem then?
Little r.
I like that. So we see it's a little bit different. And then is Z the same for every different ring?
Yes.
Yes.
Okay, so that's still the same. What's DQ?
Lambda over ds.
No,
No,
that's
no.
what's
We have to
confusing about
use
this.
Lambda.
Sigma, right?
It's, yeah, this is a 2D object. That means we have to build it up out of 2D slices. That means DQ needs a 2D charge density. It needs a sigma. Remember, this is coulombs. This is coulombs per meter squared. And this is the tricky part. If we build it up out of rings, in the previous problems, we treated the ring as one-dimensional when we were building it up out of point charges. Now we're building up a 2D object. Out of 2D slices, we need a 2D density. So that means instead of multiplying by dx or ds, I should multiply by d. What has units of meters squared?
DA.
The area. Is that okay? This
Yeah.
is weird. This is the weird part. So now what's dA? Well, if I look at my ring, that's my ring. What's the distance all the way around?
2 pi little r.
No, 2 pi little r, because it's diameter times pi, right? Diameter times pi. What's a good name for the thickness? A small amount of distance in the x, a small amount of distance in the y, a small amount of distance in the theta. What's a good name for this distance? A small amount in what? This is a weird thing to do with your fingers all over. What's that? dr, right? It's a small change in the radius. Now let's think about this. As you go to different ring radii, we expect we're going to need some sort of integral over r. So now we've got all the pieces here. Oh, shoot, what's sigma?
Isn't sigma ds? No, never mind. I'm gonna just forget that.
Yeah, it's charge per meter squared. So it's going to be,
Q over r squared.
yeah, with the
Q
constant.
over 2 pi r squared, big R squared.
Oh. The area is pi r squared. So it's charge over area.
Oh.
Right, and so 2 pi r is the circumference, pi r squared is the area. So got it? Yeah. I think we have all the pieces now. Do you think so? Let's check. We know we need to sum up all the contributions. That's what this means. What's the contribution of one ring? This. Well, what's dq for one ring? It's sigma times dA. Well, dA, I think I didn't write it down. dA is length times thickness. Does that show up? Yes.
Yeah.
Sigma is charge per unit area, right? Q over area. So now I've got all the pieces. I know what my dq is. I've got this. I shove it in. Let's see what the integral looks like. It's going to be the integral of, let's do it this way. K dq is sigma dA, which is q over pi r squared. Times dA, which is 2 pi r dr. Oh, this is a little different, isn't it? See how there's little r's and big R's now? All this over this. Is this going to be an easy integral or an ugly one?
I want to say easy.
Yeah, turns out it's ugly because R is like here, here, and here. So it's like, but we've got a table. It's on the table. So some stuff cancels, some stuff pulls out. What are the limits?
0 to big R.
Yes, because we're doing a radius integral now. So we're going from the smallest radius to the biggest radius. All right. You can crank that out and get it. Quick question. What would be different if this was a washer? What would be different if it looked like this?
You would have, you would
Total
have-
area would be pi big R minus some other R.
The total area would be different. Cole, what were you going to say? I think I heard you.
you were gonna have to adjust where you take the r's from.
Yeah, so we
the
go
little
from R inner to R outer, right? So we could kind of see the different things that might mix you up on a test day. What if this was non-uniform?
You
It
would
was
have
We're gonna have an equation for sigma.
Yeah, then sigma wouldn't be this, it'd be whatever equation I give you. What do you think?
we're screwed.
Ah, there's some more practice on page 73 for this, right? What's that? Yeah. So, yeah, let's think about this. What are you getting on test day, right? That's most of the time what people care about. You're either going to get an electric field or an electric potential integral like this, right? So you can expect something, maybe I'll go out to 3 here. Right, you can expect one of these integrals where we have to do either a voltage integral or an electric field integral. And what happens is people get used to this chapter where there's no vectors. So then I'll stick an electric field vector and you gotta go like, oh, I gotta remember the I hats and J hats for that one. I don't know, pretty straightforward. Usually, what are the shapes? Arcs, rods, rings, and washers. That's it. All right, so yeah, I think that's pretty good. And yeah,
Whether it be this problem or any problem before, I know that I'm fully capable of getting an F on all.
good, right on. How about we call this good? I think it's about time. Oh, it's time. All right, I'm calling it good. All right. Let me do it. I guess I'll end this. Hey, that's a quick way to end the class. All right, see you, everybody. Send me an email if you have any comments, all right?
See you.
Sure.
Have a good one.
Yeah, you too. And we'll see you in lab tomorrow. Do the pre-lab tonight. Do the pre-lab. Check it out.
Is
Yep.
the lab going to be in person or online?
The lab is in person. Yeah, so,
Okay.
yeah. This is helping me test this equipment, see what I think about it.
Okay.
Yep. Any other questions? Well, before I'm closing the Zoom or any from you guys here?